Okay, how's everyone feeling out there? Oh, I'm feeling the energy there, people. Try that again. How's everyone feeling today? Awesome. All right. Good to see you guys sitting on Thoughtful Thursday with a new friend. Today's lesson is about light. This stuff here that's shining on me. What is this stuff? You know, it kind of hurts your eyes if it goes into your eyes, but what is that stuff? It's a very interesting question. Like, what actually is it? Yes?
What is this light that has such small wavelength that they can penetrate?
Well, you can't use the word light when you're defining light, though, so you can't say, like, waves of light.
Waves of energy.
Waves of energy?
Because they perceive energy.
We know that, or we've been told that light is made up of, like, waves. But come on, do you see any, like, little waves? Do you see any, like, little sine curve thing? Woo! I don't.
It's so small we can't see it.
So small we can't see it, huh? Well, by the time we're done with this unit, you will see direct evidence that light behaves as if it's made up of waves. And you really can't see that by looking at light. But when all is said and done, when you see all the evidence, you will be able to make up your own mind and believe that light is made up of waves. Now, we know that when you have a wave, something vibrates, which causes something else to vibrate, which causes something else to vibrate, which causes something else, and you get that chain reaction, yes? So the question is, with light, what's vibrating in the first place, and then what actually vibrates down the chain reaction line? So, let's look at some parallels with sound. So recall, with sound waves, if you go to the root source of the sound, you'll find some sort of vibrating piece of matter. Here I'm drawing a tuning fork that has prongs that are vibrating back and forth. So sound waves are produced by vibrating matter. Well, today's lesson is about light waves. And light waves are produced by vibrating charges. So basically, if you have an electron that's vibrating up and down like this, a vibrating electron will produce light. Now, if I could scuff an electron off this tabletop and then vibrate it fast enough, it would start giving off light. Anytime you go to the source of light, you'll always find vibrating charges. So basically, the source of light, vibrating charges. It could be an electron vibrating. It could be a proton vibrating. Most often it's a vibrating electron. However, if you took a neutron and you vibrated it back and forth, it wouldn't give off any light. It has to be a vibrating charge. Now, if you have a vibrating charge, say like an electron, it actually is going to be going faster, 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 slower, 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 stop. Changing direction. Faster, 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 slower, 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 stop. Changing direction. So another fancy-dancy way of saying a vibrating charge is a charge that's accelerating. That's either speeding up, slowing down, or changing direction. What produces light? Accelerating charges. If you have a charge that's moving along at a constant velocity, it won't give off any light. Only when it's speeding up, slowing down, changing direction. Speeding up, slowing down, changing direction. Now let's go back to our comparison with sound waves. So over here we have sound. Down here we have light. Now we know with sound waves, when that tuning fork vibrates back and forth, it slaps into the air molecule right here, and it gets the air molecules to vibrate back and forth, which gets the next air molecule to vibrate back and forth, and you have a chain reaction of vibrating air molecules. That's what we talked about yesterday. So basically, a sound wave is made up of these vibrating air molecules. The question is, with light, if you have a vibrating charge, like a vibrating electron, what's out here that's actually vibrating up and down? And the weird thing is, light can travel through empty space. We know the light that comes from the sun travels through empty space as it comes to the Earth and the other planets. If it's empty, what's there vibrating, creating the next thing to vibrate, creating the next thing to vibrate? This is one model of light. Recall the electric field. That's that unit we started. We put on the brakes so we can start waves. Here's a little benefit that we started it. Okay. It's helpful in understanding light if you have a feeling for what an electric field is. We know that if you have a still charge, like an electron, whether it's still or moving, any charge alters the space all around it. We talked about how in this space all around the charge, there's an electric force field. And if we want to visualize that electric force field, we can pretend to place a tiny imaginary free to move positive charge and then draw an arrow how that tiny imaginary free to move positive charge would move. And it would be attracted. And if I put it over here, it would be attracted. And if I put it over here, it would be attracted. And if I put it over here, it would be attracted. If I put it over here, it would be attracted. This gives us a visualization of the electric field around a static charge. what we haven't studied, and it's kind of nice if we had studied it first, but due to the way, our school year unfolds, I want to get the waves done so you can do geometric optics over winter break. If we had studied magnetism first, you would have a better feel for this next piece. If you have a moving charge, say like an electron, it's moving this way. Maybe it's moving freely through space, or maybe it's inside a wire. Well, it turns out that there's another type of force field that exists around moving charges. The force field that exists around moving charges is called a magnetic force field. It's kind of weird, the shape of the invisible magnetic force field around a moving charge. The lines don't just propagate outward or inward like the electric field. The magnetic field lines always make closed loops. And basically, the magnetic field around that electron would look like a donut shape around the wire. And I try to make it like three-dimensional, showing like, where the wire is in front of the wire. Where the magnetic field line is in front and where it goes behind. To make it look a little bit three-dimensional. So basically, this shows this invisible magnetic field that exists around a moving charge. So, moving charges have a magnetic field around them. Static charges have an electric field around them. And we've been talking about what is this light stuff that moves through the air or even moves through empty space when you have a charge, like an electron, vibrating up and down. Well, it turns out that light is made up of vibrating electric and magnetic fields. If the electron that's producing the light, is vibrating, then the fields around it are vibrating as well. So here is an electron that's going to vibrate up and down. If it vibrates up and down, there's going to be an electric field vibrating up and down as well. Here you can see how the electron goes up and down. Well, the electric field here goes up and down. One minute it'll be going up over here. The next moment it'll be going down, and the curve will be shown here. The next minute it'll be going up, curve shown here. Next minute it's going down. So this little thing that's actually fluctuating up and down this way is a vibrating electric field. Now remember, the wave is actually traveling this way. So this red line shown here is the electric field vibrating up and down. But wait, there's more. Because not only is there an electric field around a vibrating charge, but there's also a magnetic field because it's a moving charge. Now, it's kind of hard to draw how the magnetic field is. When the electron goes down, the magnetic field is into the board. When the electron goes up, the magnetic field is out of the board. And of course, this in and out gets fluctuated back and forth. So as this electron goes up and down, the magnetic field is going like this. Into the board, out of the board. Into the board, out of the board. Into the board, out of the board. So I'm going to try to draw the sine curve fluctuating back and forth this way. But you need to kind of make it look like a three-dimensional picture. So here is my best attempt. And then sometimes it's helpful if you put like little lines like this. So it's like vibrating back and forth, left and right. So the blue line represents magnetic field vibrating in and out of page. Now, regardless if you look at the electric field or if you look at the magnetic field, both vibrations are perpendicular to the direction of the wave. You know, the wave is traveling this way, but the electric field is vibrating up and down this way, and the magnetic field is vibrating back and forth sideways. So what kind of wave are we dealing with when we study light waves? A transverse wave, because the vibrations are perpendicular to the direction of the wave. So we now know what produces light, vibrating charges. And now we have a little bit of an introduction to what light actually is. Vibrating electric fields and vibrating magnetic fields. That's why a fancy-dancy word for light waves, since they're partially made up of vibrating electric fields and they're partially made up of vibrating magnetic fields, light waves are also called electromagnetic waves. So it would be totally fine to say, whoa, where are my sunglasses? The electromagnetic waves are strong today. Because electromagnetic wave and a light wave, those are synonymous with each other. Let's take a look at some computer simulations of light waves. Instead of looking at my stagnant drawing like this one right here, let's look at a moving drawing here. So over here, right there, we can imagine an electron that's vibrating down, and up. This is a very, very slow vibration, and up. Actually, it would be a proton corresponding with this. And now the proton would be vibrating down. And back up. And you can see how there's an electric field that's vibrating up and down along the y-axis, and there's a magnetic field vibrating left and right along the z-axis. But which way is the wave actually moving? This way, along the x-axis. So this is one representation. And now let me show you another one that I think is moving a little faster. Again, you would have a charge right in the middle, vibrating up and down. And moving away from it would be these vibrating electric fields and magnetic fields. Another word for moving away from it is propagating. Propagating away from the vibrating charge are these electromagnetic waves, these light waves. That's what this stuff is. Now, here's the thing, though. Remember when we learned about electric fields? I told you that electric fields are basically a man-made concept to help us, kind of try to visualize what's going on, to try to model the situation. So, this is just a model for light waves. But it's still very bothersome to physicists. How can light travel through empty space? Well, the electric fields and the magnetic fields don't need a material to vibrate. Well, then, what's really going on? So maybe our understanding isn't really complete and really full. There's been a long-standing debate that there really is something there that's vibrating. And there's this name of the stuff that has to be there. And the argument goes back and forth whether this stuff is there. And the generic name of this stuff is ether. Not the kind of ether you would use to spray into a carburetor to help it start. But it's just a general term, ether. Oh, there has to be ether in between the sun and the earth. Otherwise, what's actually vibrating? So, the argument continues. And then, of course, when you hear about string theory, and where string theory says that there's more than the three dimensions and time, well, maybe the stuff is vibrating in one of the dimensions that we don't see. I know one student came up to me and said, I'm going to physics, but they got everything figured out. It's so funny. Like, we're in the dark ages, people, when it comes to so many different things. There's so much more to learn and figure out.
Is the wave like it keeps that going at infinite?
Yes. Yes.
But what about the photon?
Well, that's a whole nother aspect. Eventually, we're going to see other evidence that shows light is made up of not these fluctuating waves, but these little balls of energy called photons. The thing of it is, both of those models have conclusive evidence supporting them. By the time we're done with the light unit, you're going to have seen firsthand conclusive evidence, and you're going to say, I'm a believer. Light so behaves as if it's made up of waves. And then at the end of the year, we're going to study the photoelectric effect, and we're going to see conclusive evidence that light has to be made up of little tennis balls, little bundles of energy. Waves and little spheres are so different. Jumping a water wave at Jones Beach and having someone throw a tennis ball at you, that's two fundamentally different things. And those are the two models for life. And ultimately, what pulls them together, the umbrella of quantum theory, but that's all to come. But for now, we're studying waves, and we're going to be looking at the evidence that light is made up of electromagnetic waves. So, what if this electron is vibrated through a bigger distance? It has a bigger displacement this way. Well, then the electric field is going to vibrate through a bigger distance. And the magnetic field is going to vibrate through a bigger distance. Ultimately, when those electromagnetic waves hit your eye, it's going to get the electrons in your eye to vibrate back and forth a bigger distance.
Is that why our eyes hurt so long?
And how would we interpret that? Yes.
Well, should they say that the charge vibrates the wavelength?
No, not wavelength. This has to do more with the amplitude. Like the amplitude is like the height of the wave. So good hypothesis there. I'm glad you're thinking. That's awesome. But basically we're talking like the amplitude. The amplitude, how much the thing sways up and down, the height of the wave, what does that correspond with the light wave? Whoa! The amplitude of these light waves is too much for comfort there. The brightness of the light. Okay? The amplitude corresponds to brightness. Now, what about the rate of vibration? if the electron over here is vibrating at a slow rate, then the electric and magnetic fields over here are going to be vibrating at a slow rate. And ultimately, when that light goes into your eye, the electrons in your retina are going to be vibrating at a slow rate. But if the electrons here were vibrating at a fast rate, then over here, the electric field is going to be vibrating at a fast rate, and the magnetic field at a fast rate, and the electron in your eye is going to be vibrating at a fast rate. And how do we interpret the different rates of vibration? How many cycles per second? Take a guess. Anyone want to take a guess? I'm not looking for a number. I'm just looking like, how do we interpret that? You know, the rate of vibration with sound, if I vibrate your eardrums with a slow vibration, hey, how you doing? And if I vibrate your eardrums with a high rate of vibration, but what about with light waves and the number of vibrations per second? Color, exactly. Okay. If the electron is vibrating at a slower rate, the color looks sort of reddish. If, noticing zone, if it's vibrating at a faster rate, it would be more violet.
What would be white?
White is actually a mixture of all the different colors. So it's a combination of all of them vibrating. And blackness is an absence of the light. No light at all. So basically, the frequency, remember, frequency is the number of waves per second. The frequency corresponds to the color of the light. The electrons on the surface of Kern's blue jacket there are vibrating back and forth faster than the electrons that are vibrating off of this red lab notebook. When we come back, we're going to have to make a whole little chart showing the different colors, and then there's some light that the frequency is so high that the light is still there. It's just that our eyes can't sense it. Our electrons cannot respond fast enough. We can't see it, so it's invisible to us. And there's light that the frequency is so slow that, again, our eyes don't respond to it, and we can't see that light. So when we come back, we'll look at visible light and invisible light. Mwah. We're going to find out right now. Okay. So, basically we have visible light. And visible light starts off with a low frequency red light. All the way up to violet light. So we're talking 4 times 10 to the 14th hertz to 7.5 times 10 to the 14th. Yep. And of course, in between red and violet, you have orange, yellow, green, blue. Now, remember we talked about the frequency of sound waves? And if there was a sound wave where the frequency was just above human range, and we couldn't hear it, the frequency was just too high. Remember what those sounds were called? Ultrasonic. Similarly, with light, if it's just above the range that our eyes can handle, guess what kind of light we're dealing with? Ultraviolet light. Ultraviolet light has a higher frequency. The light is still there. You still have vibrating charges producing vibrating electromagnetic waves. Just that our eyes can't respond to it. Ultraviolet light is responsible for giving you sunburns, skin cancer. Then if you go to an even higher rate of vibration, a higher frequency, you have X-rays. The interesting thing about X-rays, this invisible light can actually travel right through human flesh. So if these light rays shining on me right now were X-rays, my shadow would not look like the shadow right now behind me. However, what can't X-rays travel through? What else inside the human body? Bones. So basically, if you stood in front of X-ray light, you can't see it, of course, frequency's too high, but the X-rays can go through your flesh, but they can't go through the bone. So basically, what would the shadow look like? Your skeleton, your bones. And that's what they do. They put film there, and basically, you end up seeing where the X-rays didn't get through. That's where the bones are. And then if you go higher frequency yet, you have gamma waves. So these are all light waves. It's just that the ones between red and violet are visible, and these up here are invisible. Likewise, if the charge is vibrating too slowly, the light's still going to be there. We just can't see it. And if you go lower than red, what do you have? Infrared. Infrared light is associated with heat. Anything that has a temperature, including you, me, anything that's alive, that's warm-blooded, gives off this invisible light, this infrared light. The military has goggles that takes the infrared light, can increase the frequency to red light so they could see. So in a dark room with the lights off, everything sealed, you wouldn't be able to see any of you. You put on those goggles, you would see a red outline of every single one of you. You're all giving off this invisible infrared light. You're giving off this sort of heat. I know growing up on the farm, we had those heat lights, and they shined infrared light on like a baby calf in the wintertime, to keep it warm. And basically, it wasn't pure infrared light, because if it was pure infrared light, you wouldn't see it. And I think it would be too expensive to make pure infrared light. But basically, it was probably a mixture of infrared light and reddish light and orange light all mixed together. But another use for infrared light, all your remote controls. I actually shine invisible light up there. Boop. Don't want to do that. So when you're doing your remote control, you're actually shining an invisible light beam, to your TV. And eventually we're going to learn how light waves reflect off of things. So I'm always trying to see if I can get the remote, and sometimes I can in some places, to like bounce off the back wall and then still get the TV to work. So I'll go, sometimes it works, sometimes it doesn't. Now, if you go even lower frequency light, you have microwaves. Microwaves are invisible light waves. Now, I've had students say, Mr. S, I can see the light inside the microwave when I turn it on. Well, that's because they put a visible light in there as well. The actual light that's heating up your food is invisible. It's microwaves. Gamma waves are high frequency. That's a good question. I can't think of a use right off the top of my head. Now you got my interest on it. We'll have to look into that. Microwaves, this invisible light, have the just right frequency, the just right mode of vibration, that when this invisible light hits the water molecules on the surface of the food, it gets the water molecules to vibrate, and that ends up heating up the food. And last but not least, and this is the one like people mess up the most on, they start to think it's a sound wave, but it's not. It's an invisible light wave. Radio waves. Radio waves are invisible light waves so if you have like the Syosset radio station and they're broadcasting from here, what actually travels from that antenna out at the front of the school to the local radios are invisible light waves, radio waves. How fast do they travel? The speed of light. They're light waves, people. And then you have your little radio. And when that invisible light hits the antenna, it gets the electrons on the antenna to vibrate the exact same way, the mimicking effect, as the electrons were vibrating in the antenna in the first place. And that signal ultimately gets the cardboard cones there to press in and out at the same rate, which starts slapping into the ear molecules, which slap into the next ear molecules, and now we're dealing with sound waves. But what actually goes through the ear from the radio station to your antenna? Invisible light waves. And people start to think that they're sound waves because they're called radio waves. But they're not. They're invisible light waves. So there you have the whole spectrum. And all together, this whole thing, and as you go this way, you have a higher frequency. And all together, they're all called electromagnetic waves. Now remember yesterday we talked about how fast sound travels? And sound does travel pretty fast. I don't know if you've ever been in a car and the car was doing like maybe say 80, 85 miles an hour. That's fast. You start going faster than that, like that's dangerously fast. If you're going 100 miles an hour, very, very fast, very, very dangerous. Well, sound travels at the speed of 750 miles per hour. Way faster than the speeds we're normally dealing with, yes?
Have they made a car that travels at the speed of sound? Or is that only fast?
They have made a land vehicle that has gone. I didn't know they run it through the flats of
Arizona.
Yeah, Arizona. Basically, ladies and gentlemen, when you compare the speed of sound with the speed of light, though, the speed of sound is like the turtle. Okay, 750 miles an hour. Light travels 186 miles, 186,000 miles, not in an hour.
In a second.
In a second. 186,000 miles in a second. It would travel here to California and back 30 times in a second. 1 second.
Wait. I read somewhere that in the blink of an eye, light can travel 7.5 times around the world. Is that true?
Sounds right. But of course, when you're doing your problems, you're going to use the SI units, the System International units, the metric units, 3.0 times 10 to the 8th meters per second. So you have to be careful, because you might read a problem in the textbook, and the problem might just casually mention that you're dealing with X-rays. Well, as soon as they casually mention that, the problem's pertaining to X-rays, you think, oh, that's a light wave? You put down the speed of light. That's how fast X-rays travel. They all travel at that speed. All the different frequencies. So hopefully that gives you a little bit better feeling of what light is. It's made out of it's made from vibrating charges, accelerating charges, and the wave itself is fluctuating electric fields and magnetic fields.